Hello everyone, this is András Kovács, and in this talk I will talk about large and infinitary quotient inductive-inductive types. This is a joint work with Ambrus Kaposi. First, let's do a quick overview on what this work is about. We give syntax and semantics for a general class of inductive types, and we cover a number of interesting new cases and features, including inductive definitions of real, serial, and ordinal numbers, and also large eliminations. We also show that every large infinitary QIIT is constructible from just one such QIIT. And we also care about mechanized implementation, and we try to keep our syntax and semantics fairly close to what's needed in a proof assistant. So for example, the encoding overhead of signatures is small, so the signatures that can be specified in our system are fairly close to how we would write an inductive signature in Kok or Agda. And it also holds that the semantics computes induction principles strictly as expected. This is also quite important in an implementation because we want to be able to just plug in a specification of an inductive type and just get out an induction principle. So it should be possible to write a computer program based on our work which does exactly this. We built on our previous work, which handled small and finitary QIITs. The generalization from the small and finitary case to the large and infinitary case is fairly technical, and I will not go into those technical details much in this talk. Instead, I will try to focus on the big picture and the general approach of this work. And you can look at the paper for the gory details. Inductive types are a common way of extending type theories with classes of freely generated structures. An inductive signature is a syntactic description of an algebraic structure. For the semantics of a signature, there should be at least a notion of algebras and homomorphisms, which form a category, and there should also be an initial algebra, and such an algebra corresponds to an inductive type. For example, this particular signature is the signature of natural numbers, and the semantics of this signature should be the category of natural number algebras, and the initial algebra should correspond to the usual type of natural numbers in some type theory. Let's move on to quotient inductive-inductive signatures. The general approach in this work is that a signature is just a context in some particular type theory, which is called the theory of signatures. And the theory of signatures is formally given as a category with families extended with certain type formers. In this slide, and also on subsequent slides, I will introduce these extra type formers in order. So first, we have a universe, which is a type in any context, and we also have a decoding operation for the universe. And we also have a function space, and the distinguishing feature of this function space is that the domain is restricted so that the domain has to be in the universe, but the codomain can be an arbitrary type. And we also have some term formers which are omitted from here, like lambda and application. And let's see an example signature, again for natural numbers. So here we have a typing context, and we start with the empty context, and then we extend the context with something which is in the universe, and then we extend the context with 0, which has type EL of not, and we also extend the context with this successor, which is a function from not to not. And note here that the restriction of the function space ensures that we can only write down strictly positive signatures, because U does not contain a function type, so it is not possible to write a function on the left side of this function arrow. The theory of signatures has an identity type, and you can see here that the universe is closed under this identity type, and this is an extensional identity, so we have uniqueness of identity proofs, and we also have equality reflection. Now we are able to write down a signature for categories. So here we have a typing context, and you can see that it contains a type of objects and also a family of morphisms which is indexed over objects for the domain and the codomain. And we also have identity morphisms and composition. And here we have the left identity law, which is an equation. So this particular signature is inductive-inductive because here we have a type which is indexed over another type in the signature. And it is also a quotient signature because it contains an equation. So you can observe that we need at least Infinitary Quotient Inductive-Inductive types if you want to talk about free categories with extra structure. And if we only consider this signature, then the free category is just the empty category, which is not that interesting. But usually syntaxes of type theories are also categories with extra structure. And so if we want to talk about them, then we really need QIITs. Now we make it possible to have infinitary constructors in signatures. So in the meta theory, we assume that we have universes and function types and also natural numbers. And here we have a rule which says that the universe in the theory of signatures, so this U, contains a function space, but this is a special kind of function space because the domain is given as a meta-theoretical type and the codomain is given by a meta-theoretical function. So for every x in A, we have a term in the theory of signatures which has type U. So here the dependency of the codomain on the domain is given by a meta-theoretic function. So if we write something like lambda x dot bx, then it's a meta-theoretical function, and this bx is just notation. So one example for this is the type of infinitely branching trees. So here we have the type, and here we have a leaf constructor, and we also have a node constructor, but we are using the infinitary function space here in the node constructor. So here, this arrow is the inductive function space, which we have seen previously. And now we are able to write a function arrow on the left of this function arrow. So here, we can write an infinitary function arrow. And this is possible because U contains this function arrow. But this is still strictly positive because the type of natural numbers is meta-theoretical. So it's not something which is internal to this signature. And we can also combine infinitary constructors with equations in the signatures, and then we get infinitary QIITs. And examples for such QIITs are real numbers from the homotopy type theory book, and also some formulation of ordinal numbers, and also a partiality monad. We have a third and final function space in the theory of signatures, which we call the external function space. This is quite similar to the infinitary function space. The differences are that the codomain is not necessarily in the universe, so the codomain is a proper type, and the external function space itself is also not in the universe and a proper type. So it is not possible to write this kind of function arrow on the left-hand side of an inductive function arrow. This makes it possible to add meta-theoretic parameters to constructors in a signature. For example, here we have a signature for trees, which can branch with arbitrary meta-theoretic sets. So here we have an external parameter, which is something in set 0. And then here we have an infinitary function type. And then here we have an inductive function type. And this signature can be called a large signature because here we have a domain type, set 0, which has type set 1, so it's not a small type. Examples for large infinitary QIITs are surreal numbers, again from the homotopy type theory book, and cumulative hierarchy of sets from the same book. And also, interestingly, the syntax of the theory of signatures, which we are discussing right now. So it is possible to give a signature for the theory of signatures inside the theory of signatures, and we may call this self-description or levitation, as in the previous work, and we can have this self-description up to some bumping of universe levels. So signatures at a given universe level are able to describe signatures at lower universe levels. And this is fairly technical, so we omit the details of universe levels in this talk. Again, you can look at the paper. The theory of signatures is large and infinitary for the following reasons. First, it is large because, for example, in this rule, we refer to a set I, which is an arbitrarily large meta-theoretical type. Second, it is also infinitary because here we have a branching which is given by a meta-theoretical function. So if we have a syntax for the theory of signatures, then it would also look like an infinitely or potentially infinitely branching tree. Later in this talk, the ability to do self-description will be very useful. Here we have a bit of a problem. The theory of signatures can be given as a large infinitary QIIT, as we have seen, but at this point we don't know anything about the semantics and the existence of such QIITs. We are only in the process of trying to work out such QIITs. There are some possible solutions to this issue which are fairly unsatisfying. First, we could define the raw syntax of signatures together with well-formless relations, and this was used by Cartmel for specifying signatures for generalized algebraic theories, and this is also kind of a conventional and old-fashioned way of presenting syntaxes of type theories. But working with raw syntax is very tedious and very complicated, so we would like to avoid doing this. Another solution is to give signatures by an ad hoc QIIT, which is postulated to exist in the meta theory. And this was used in our previous work, which concerned small finitary QIITs. But needless to say, this solution is also fairly unsatisfying. Fortunately, there is a fairly nice solution here. So the key observation is that we don't actually need the syntax or the initial algebra for the theory of signatures, because we only want to write down signatures and give semantic interpretations to those signatures. So we can use something which looks a bit like a church encoding. And we say that a signature is a context in an arbitrary algebra or model of the theory of signatures. So a signature is an element of a meta-theoretical function type, which looks like this. And then with this church-like encoding, it is possible to interpret a signature in an arbitrary model of the theory of signatures by simply applying it as a function. Let's move on to the semantics of QIITs. So we give a model of the theory of signatures, which looks in the following way. Contexts are interpreted as finitely complete categories. Types are isofibrations over their contexts. Substitutions are weakly finite limit preserving functors. And terms are sections of isofibrations, which also weakly preserve finite limits. And in the paper, we use a type theoretical flavor of these above definitions. Instead of finitely complete categories, we use categories with families with certain extra structure. And this definition, which we actually use, is biequivalent to the usual notion of finitely complete categories, but it computes induction principles more strictly. So as I mentioned before, we care about being able to write just a program which computes induction principles as expected, and it is not really ideal if you can only compute induction principles which are isomorphic in some way to what we would like to have in a proof assistant. And also, isofibrations are based on displayed categories. And this makes type substitution strictly functorial in a very easy way, so we don't need any extra strictification step. And the strictly functorial type substitution works similarly to the original cubical set model of Martylov type theory. Let's continue with the presentation of the model. The empty context is interpreted as the terminal category. Context extension is taking the total category of an isofibration. And remember from the previous slide that types are interpreted as isofibrations. U is the category of sets, and EL, which is the decoding operation for the universe, is interpreted as discrete isofibration formation from some set-valued functor A. The identity type is interpreted as some kind of equalizer of T and U, And this is not a very complicated definition, so it's basically just pointwise equality of t and u. And then we have three function types. So we have the inductive function type, which is interpreted as a dependent product of isofibrations. And the external and infinitary function types are interpreted as A-index direct products. In the external case, it's a direct product of isofibrations. In the infinitary case, it's a direct product of set-valued functors. So the interpretation of the external and infinitary function types are fairly simple, and it's a bit more complicated to give interpretation for the inductive function type. It's interesting to note that this is kind of a directed model, because we have a type theory and a model such that contexts are interpreted as categories. And in general, the directed models can be very complicated because of problems with the variances. But here we avoid all such complications arising from variances. So first, our types are invariant because they are isofibrations. And second, the universe only contains discrete fibrations. And the inductive function type also has a discrete domain. And this discrete domain makes it possible in the first place to give this model. So if we don't have this strict positivity restriction on the domain, then it would not be possible to give this model at all. Let's look at an example for getting the semantic interpretation of a signature. So here we have the signature for natural numbers, which is a context in an arbitrary model of the theory of signatures. So what you see here is built out from the components of an arbitrary model. And then we instantiate this signature to the previous M model. And from this we get a finitely complete category where the objects are natural number algebras. And the morphisms are functions which preserve zero and successor. So the morphisms are natural number algebra homomorphisms. And we recover a notion of induction principle from finite limit structure. And we also get as a general theorem that an object is initial if and only if it supports induction. Now we can repeat the same for the theory of signatures itself. First, we write down a quotient inductive-inductive signature for the theory of quotient inductive-inductive signatures. And we can remember that the theory of signatures is given as a category with families plus some extra type formers. So here we can see a fragment of a category with families, and it is also possible to include in the signature every type former which we previously discussed. Now we can take this signature and interpret it in the M model and get a finitely complete category of TOS algebras. And from that, we get the induction principle for the theory of signatures. So now we can assume the existence of the QIIT for the theory of signatures, which is just the initial TOS model or TOS algebra, and then do constructions by induction on syntactic signatures. And here by syntactic signature, I mean a signature which lives in the QIIT for the theory of signatures, so not the church encoded notion of signatures, but rather something which is in the syntax. It's interesting to note that basically everything which we had to manually specify about the theory of signatures in this work is actually just the notion of model for the theory of signatures. So if we can write down this signature, then everything else which we need later is just going to fall out automatically from the semantics of quotient inductive-inductive types. One particularly interesting construction which can be done by induction on syntactic signatures is the construction of term algebras. We construct all QIITs by induction on the syntax of signatures. How does this work? So every sort or type constructor in the QIIT arises as a set of terms in the syntax of TOS. For example, we can again take the signature for natural numbers, which is just this typing context, and then consider terms in this context with the type EL of not. And the set of all such T terms is isomorphic to the set of natural numbers. The reason is that the only way of constructing such T terms is by doing finitely many applications of successor to 0. What about quotient types? For this, let us consider a very simple signature with an equation. So this is a signature for the quotient interval, but we don't really consider higher dimensional types in the semantics. So a quotient interval is just isomorphic to the unit type. But let us consider the terms in this context with the type EL of int. And again, the same construction works as before, because here we have the equality reflection rule for the propositional equality type, which causes the terms in the syntax of the theory of signatures to be quotiented by all the derivable equalities. So here, because in the context we have this equation, we basically get the right amount of quotienting. So the term model construction still works the same way as before. The term algebra construction shows that we can reduce every QIIT to a fairly large and complicated QIIT, which is the syntax of the theory of signatures. Now the question naturally arises, can we do better? So is it possible to reduce every QIIT to some simpler type formers? One thing which we could try is to construct the syntax of the theory of signatures from simpler type formers, and then, because TOS is constructible from simpler type formers and every QIIT is constructible from TOS, we can compose the two constructions to get a reduction of all QIITs to some simple type formers. This task is an instance of the initiality construction popularized by E5.C. The original motivation for the initiality construction was to provide some kind of moral justification for the usage of raw syntax. However, in our case, this construction is not only interesting because of philosophical reasons, but it also has some ramifications on the reducibility of QIITs. There's a bit of a complication in this construction, because it was shown by Lamstein and Schulman that infinitary QIITs are not reducible to the combination of inductive families and simple quotient types. So it seems that infinitary QIITs are not a conservative extension of extensional type theory, and they seem to be equivalent to some constructive choice principle. But currently we don't really know what is the right formulation of this constructive choice principle, but it is very likely that it is going to manifest as some kind of simple infinitary quotient inductive type. With this, we have reached the end of this talk, so thank you for your attention.